Hello everyone, welcome back. In this next series of videos, there will be 3 videos, maybe 4. We are going to talk more deeply about buffer solutions. In the titration videos, we talked through what happens in the buffer region of a titration and what a buffer is. But it turns out that we can make buffers and use buffers in a lot more ways than just as part of a titration. And so in this next series of videos, we're going to kind of walk through some of the things that we often do with buffers. Now, these videos are going to be really helpful whenever you start working on the buffer assignment, which comes during the last week of March. So starting around, I think around March 30th. Let me check my calendar real quick. Yeah, so the week of March 30th is when the buffer assignment will be posted, and these videos are going to be very helpful for that. So let's get started. Okay, so the first thing we have to remember is what is a buffer? Buffers are solutions where the concentration of the acid and its conjugate base are within a factor of 10 of each other. And so that means that in a solution, we have a weak acid and its conjugate base, or we can also have a weak base and its conjugate acid. And for it to be a buffer, the concentrations of these two have to be pretty close to each other. A factor of 10 is reasonably close. When we create a buffer, the reason we create buffers is because the resulting solution resists changes in pH when diluted or when acids and bases are added to the solution. So remember our titration curve, where we had our volume of HCl and we had our pH, and we had this sort of flat region, and we called this the buffer region. And so what this region is a buffer exists in solution, and we can see that it's resisting changing its pH because as we add HCl, the pH is not changing significantly. Okay? We can calculate the pH of buffers. Remember that this is an approximation, but it's a very good approximation. But very good. And so we can calculate using the Henderson-Hasselbalch equation, where the concentrations that we plug in for the weak acid and its conjugate base are initial concentrations rather than equilibrium concentrations. Okay, so let's think about how we can make a buffer. One way of making a buffer is creating 2 separate solutions. And so in this example, we have 5 milliliters of 0.01 molar acetic acid, CH3CO2H. And we have a solution that is 5 milliliters of 0.010 molar sodium acetate. And so one way of making a buffer is creating these 2 solutions and mixing them together. And so we would get 10 milliliters of buffer. And this question is asking, if I do this, what is my pH? of this new buffer solution. Okay, so we want to find the pH. So let's get to work. So we know that this problem is talking about a buffer because I have an weak acid and its conjugate base. And so when I mix these together, that is going to create a solution that has both, which means that it is a buffer. And so since we have a buffer, we know that we can use the Henderson-Hasselbalch. pH equals pKa plus the log of the concentration of the conjugate base divided by the concentration of the weak acid. And so to solve this, the first thing that we are going to need to know is the pKa of acetic acid. And so remember that pKa is equal to minus log of the Ka. And if we look up the Ka for acetic acid and we plug this in, we find that the pKa is equal to 4.7. The next thing that we need to know are the concentrations of the acetate and the acetic acid. So, and we want to know what those concentrations are in this buffer. And so we need to know our CH3CO2 minus concentration, and we need to know our acetic acid concentration. And so when we go mixing these, we do a dilution. And so to get our concentrations, we're going to have to use our dilution knowledge. And so to find this, we're going to use M1V1 equals M2V2. And so my starting molarity is 0.010 molar. My starting volume is 0.005 liters. I want to find my ending volume, I want to find my ending molarity, and my ending volume is 0.01 liters. And so I get my new molarity as 0.005 molar. Now, I'm going to do the same thing for the acetate concentration. CH3CO2 minus M1V1 equals M2V2. And so I have my initial concentration is 0.01 molar. My initial volume is 0.005 liters. I want to find my new concentration if my total volume is 0.01 liters, and I get that M2 is 0.005 molar. So now I have the information that I need to put into my Henderson-Hasselbalch equation. So pH is equal to pKa, which is 4.7, plus the log of the concentration of my acetate, which is 0.005 molar, divided by my acetic acid, 0.005 molar. And so I find that pH of this solution is 4.7. Okay, so on the next slide, I'm going to do another example. Okay, so in this example, I have mixed 2 milliliters of acetic acid with 8 milliliters of sodium acetate. So I have the same sort of problem happening where I'm going to create a buffer, and so I can find the pH of a buffer as pH equals pKa plus the log of the concentration of the acetate. divided by the concentration of the acetic acid. And so to solve this, we're going to have to find the concentration of the acetate. And since we're mixing two solutions together, I'm going to use the dilution. And so I'm starting with 0.01 molar. I have 2 milliliters of that. I want to find the new concentration, and I'm making a total of 10 milliliters. And so M2 of the acetate is going to be equal to I used the wrong numbers here. This is acetic acid. We're just going to cross it out and make this be acetic acid. Let's clean this up a little bit since I wasn't paying attention to what I was doing. So M2 is equal to 0.0020 molar. And let's do the same thing now actually for the acetate. So I've got M1V1 equals M2V2, and so I've got 0.010 molar, 8 milliliters is equal to M2 is what we want to find, and I'm making a total of 10 milliliters, and so I get that M2 is 0.008 molar. And again, we're working with the acetate, and so we find that the pKa is equal to minus log of the Ka, which is equal to 4.7. And so pH is equal to 4.7 plus the log of, we do the base, so 0.0080 divided by the acid, 0.0020. And if I solve this out, I get that the pH is equal to 5.3. Now to sanity check this, what I do is I compare my pH of my solution to my pKa. So we know that when the concentration of the base is equal to the concentration of the acid in the solution, that the pH is equal to the pKa. So in this case, our concentration of our base is greater than our concentration of our acid. And so therefore, I would expect my pH to be greater than my pKa. And that is what I see. And this is because there's more base in there. So in this buffer solution, there's more base than acid. And so it should be somewhat more basic than whenever the two solutions have equal concentrations to each other. Okay, so in the next video, I'm going to walk through how we create buffers using solids instead of solutions. And so stay tuned, keep asking lots of good questions, keep coming to office hours, keep seeking your resources. I hope you're finding these videos helpful, and if you're not, there are plenty of other resources that you can find on World Class. So let me know how I can help, and I will see you in the next video.